Hello and welcome back to another episode of the Natural Number Game using Lean4. Today we'll be starting the multiplication world, building off of our work last time in the addition world. So first thing is we're going to want to define a couple of axioms using the definition of multiplication. As a reminder, here is our definition of multiplication, and I realized that we didn't need this extra rule of successor of 0 is just m when we multiply m and n because, well, that's kind of just built into this rule here. So when we're multiplying, for example, 1 m by 1, well, we get m by successor of 0, so we add m to multiplication of m and 0, and that's just m. Cool, so let's start by importing relevant things for the natural numbers. And let's start by defining a couple of axioms. We're going to have my multiplication by 0, where we take a as a natural number. We say a times 0 is 0. And we can prove that reflexively because, like we see the definition here with our recursion or induction on n, where we see that if n is 0, we get 0, n is 0, or the second thing to multiplication is 0, so we get 0 by reflection. Similarly, we're going to have the same thing done for the successor case. So if we have a, we're just kind of writing out what this means. So if we have m times successor n, or a times successor b, that is just adding m plus m n prime, so in our case a plus a times b, again by reflection. Cool. With these two lemmas, let's prove something a bit more interesting. We're going to prove 0 mole zero times m is equal to 0. Well, we can't prove this by reflection because, well, that's not how the function set up. The function setup is anything times the second parameter. If the second parameter is 0, the image is 0. If the first parameter is 0, we don't really know what to do. All we know is we're gonna have a bunch of add zeros, and we should treat those. Let's think how to do this. Well, I'm thinking we're going to use induction. By induction. How to do the induction again? Induction using R. So induction N using MD. Let's see how we did it. By induction N with, okay. By induction on M with a couple of cases, 0, successor M prime. Okay, so in this case, we have 0 times 0, and well, we could just do that by rewriting mul 0. That takes care of that case, and then for this one, we have the hypothesis that 0 times m prime equals 0, and we have the case it's 0 times successor of mn. What happens when we apply mul successor? So now we have 0 plus 0 m prime. Okay, let's apply our hypothesis. How do we access our hypothesis again? Let's see what we did. Oh, we need to add induction hypothesis to give that a name. So mul successor, and then inductive hypothesis, and then add 0 from our addition world, or 0 add. But we need to import my.nat.addition world to get access to, or add 0. Either one should work. And ta-da! We have our lemma for 0 multiplication, or like 0 times any number m. First level done. Now let's move on to mul1. As the name suggests, we're going to be multiplying one by m. Mul by 1. Okay. M times 1 equals m. Can't do reflexively. What's this? Failed to synthesize. Oh. We need you to be also a MyNet. Oh, I spelled this wrong. Cool, that just works reflexively. Okay, even though the reflexive one works, because I'm guessing if you just expand the definition of what multiplying is by 1, it just ends up equaling m. I'm going to try to do this a little differently by starting with the theorem we had last time. 1 equals successor 0 from the addition world by definition, and then here we have m, so we go from m times 1. Okay, if we try to apply the theorem mul successor to this, well, we get an error because we don't have the pattern something times successor something else. We have the pattern m times 1. Well, we know 1 is successor of 0, so what we could do is after 1 equals successor of 0, this transforms it to m times successor of 0 instead of m times 1. And then we could also now apply mul successor. And now we have m plus m times 0. We can apply mul 0. And then we can apply add 0. And we're done. Cool. moving on to the next level in the multiplication world, we have lemma mol of 1 mol m minat 1 times m equals m. Okay, by since we don't have a mole successor lemma, I don't think we can just expand it out, because we only have lemmas of the form a times successor of b, not b times successor, or not successor of b times a. I guess we could do 1 times successor of m prime maybe, and think how that would be expanded out, but that would just be 1 times 1 plus 1 plus 1 plus 1 m times. That would be hard to prove without just using induction, so I think we're going to use induction again. 0 successor m prime, inductive hypothesis. Okay, I'm guessing the first one should be easy. 1 times 0 equals 0. Well, that's just by mol 0. Okay, for this case, 1 times successor m prime equals successor of m prime. And with the inductive hypothesis of 1 times m prime equals m prime. Well, this is in the form of a times successor of b, so let's try to mol successor 1 plus 1 times m prime equals successor of m prime. Okay, we should probably end up using successor equals add 1, so, but first we can apply our inductive hypothesis. 1 plus m equals successor m. Now we can apply add commutative to switch them in the right order, and then apply the successor equals add 1. Heck yeah, and I think if we didn't have the add commutative it wouldn't work. Yeah, because it wouldn't match the pattern. Or I guess it would just, like, yeah, on one side be one thing, on the other side be another thing, so we need add commutative. Cool, that's 1 mol. Mol add lemma mol add. So now we're doing a lemma for how multiplication interacts with addition. So we're going to have T, A, B, all be naturals. We want to show that T times A plus B equals T times A plus T times B. By something. Okay. T times A plus B equals T times A plus T times B. And see, it's T times the form of something. Maybe we can use induction again. Let's see where induction gets us. Induction, probably on T. Induction T with 0. And successor of T prime. Okay, Zero case should be not too bad. Well, that'll just be 0 all around. Let's look at the inductive case first, though. I'm unsure if this induction will work. I might have to switch to another tactic or idea. Okay, so our inductive hypothesis is T prime. Oh, we have a bunch of successors. Successor of T prime times A plus B. Well, we don't really have successor on the left usually. But we do have successor is something plus 1. So maybe we can use that. Okay, we got a bunch of add ones. Can we distribute somehow? T plus 1 times A. I need to do some thinking.
Going. So I'm going to stream the natural number game, and I should perhaps do that. There, and now the goal has become suck A equals suck A. So this goal here we can solve by reflexivity, right? What does reflex that? Let's go to multiplication world, because I could, yeah, why not? L1 is 2. So let's try proving it with Rettel. And now mul 0, I guess mul 0 is also true by definition. Rewrite mul 0. That's true by definition. Oh, I forgot the comma. Don't forget the comma. This is true by definition. There. And cat. That's a generic word for a cat. Thank you very much. That's and now I want my tick. Thank you very much. Mul add. Yeah, I'm sorry, Kitster. Mul add. Oh, yeah, I see. Distributivity. I need to prove it by induction on something. I'm really concerned. I don't have suck mul. Why haven't I proved suck mul yet? Suck mul looks really important. If I had suck mul, no, Kitster is, and that's short for cat. That's a generic word for a cat, isn't it? My cat is called Squidgy Gravity Epcirc the Third. Squidgy Gravity Epcirc Buzzard the Third, because we got her just after I got an Epcirc grant. But everyone just calls her Kitty, or Gravity, which was my daughter's name for her when she was like 4. My cat is called Gravity. I'm going to do induction on. I think induction on T is doomed to failure. Induction B with DHD. Right, let's see if I can get through this stuff quickly. So this might be true by definition. Let's try. Is it true by definition? It is. And now this one here. Let's try sim add.
Okay, let's use the suck add from the additional world. What do we have? Rewrite failed. I don't know the pattern suck question mark A plus B, don't we? We have A plus suck B prime. So let's add commutative first. Okay, that gets us this. And then T times successor B, we know how to deal with that. Mul successor. T plus B prime plus A. I guess we can add commutative B prime A. And then we can apply our deductive hypothesis. Okay. That's getting us somewhere. Now I want to move the parentheses. How do I move parentheses? Add commutative AB. Add associative. What's add associative? Yes, we want add associative. Oh, we want to do it in reverse. Does that work? Yes. Okay, now we have T plus T times A plus T times B prime. Okay, now we want to get T to the B prime side, so we can swap these two with add right commutative. Oops. Add right commutative. What do we have now? T plus TB prime. Okay, now for that, we can finally apply mul successor in reverse. And then we can add commutative. And we're done. Okay, now let's take care of the zero case. That one should be a lot easier. Okay, T times A plus 0 equals T times A plus T times 0. well, we could just rewrite mul 0, add 0, add 0, and we're done. Nice. Okay, that one was quite a long proof. Maybe there's probably a shorter way to do mul add, but this is what I was able to do. And yeah, we proved a handful of interesting lemmas, starting with our 2 axioms, and then we're going to do more next video. And in the next video, we'll do some more stuff with multiplication and get up to commutativity and associativity of multiplication. So stick around and watch that video after this one. Thanks for watching.